always ready.
Always ready. I presume that you saw the homework?
Took a brief look at it on the way up here this morning. Yeah, I got it 20 as well.
All right. It's only 3 problems, and they're actually kind of short for quantum problems. So this should be one of your less rigorous weeks as far as homework goes. After making them, I looked at hyperphysics and saw, wow, hyperphysics does exactly problem 1. You still have to show how it's done, you know. But yeah, I figured there's probably places that do it because number 1 is real simple. Well, real simple in concept. How do you know what's the most probable radius in the 1, 0, 0 state, and what's the expectation value? And it's still a good problem to do. And the reason I did 1, 0, 0 is because the math is easy. It's the same principle. Why choose one that has hard math to show a principle? And heck, I don't even remember what the other 2 are. I assume that we'll have our office hours tomorrow.
Actually, I have a physical for my mission trip tomorrow morning, so I won't be here.
What about you, Andy?
And I'll try to make it tomorrow.
Okay.
It just depends on how late I work.
All right.
I work pretty late usually on Monday nights. So.
I am curious, where are you going on your mission trip, Chris?
At first I was going to Cuba, and then they canceled that trip, and now I'm going to Indonesia. So there's an orphanage over there that we're going to for May.
That sounds good. I'm trying to remember how close that is to the oil slick. The oil slick's out in Borneo. Borneo's part Indonesia, part Malaysia, right?
Yeah. Somehow over there. My geography in that region's not the best.
It'll get better.
All I know is I'm prepared to get either traveler's diarrhea or malaria, which is one of the 2. Something always happens, so I'm going under.
I would prepare for neither. I mean, nobody wants. I just lost 10% of my body weight out in my rear. Is not, not the way I want to prepare.
It happened to all of us last year in Egypt.
Okay.
Our entire mission trip, everyone just got sick for like 4 days.
That is less than optimal. Okay. Does this picture ring any bells to you? I know it's high quality graphic. I tried to duplicate this in my physics class just before this because we're getting to that area where we're talking about the same thing. This is a diagram illustrating the relationship between total angular momentum and the orientation of the angular momentum. So we have learned that total angular momentum, we haven't learned. We'll learn today, much more rigorously than we did with my class the period before, that total angular momentum is h bar square root of L times L plus 1. And that L in the z direction is equal to h bar times m. And so this is taking the special case, just the randomly chosen case, of let L equal 2. So that means I should write it on this side. So L sub 2 is equal to h bar square root of, and we can do this in our head. 2 times 3 is 6. We're pretty good at this math, right? Okay. And so in this diagram, we have a semicircle drawn with a radius of square root 6 h bar. And then we say, well, the L sub z values, which is the component of the total angular momentum that's parallel to the external field. The z direction is equal to the direction of the external field. That's what z direction means, okay? So we simply define the z direction as the direction of our external field. Randomly chosen, right? I could put a magnetic field like this, then z is up. I could put a magnetic field like this, then z is to the right. And so I take my atom, I put it in a magnetic field, And the orientation that's parallel to that magnetic field could be 2h bar. This is for m equals 2, right? Or it could be h bar, 0, minus h bar, or minus 2h bar. Why not 3 or minus 3? Well, we saw mathematically a reason why m has to be between plus L and minus L. Or we can see here that 3h bar is bigger than the total angular momentum. You can't have the angular momentum in the z direction is bigger than the total. So two useful ways of recognizing, yeah, there's a limit. And so you can actually determine, see this here is hard to read. That's as much zoomed as I can get. The angle between the z-axis and my angular momentum can be determined simply by taking the hypotenuse in all of these cases is square root of 6h bar. And here the adjacent side is 2h bar. If I were to go down to this one, it would have been h bar. And so I can put cosine is adjacent over hypotenuse. I called it phi because it's azimuthal angle is equal to so there's a general equation, and of course the h bars cancel. There's a general equation to tell us the angle between the angular momentum and the external magnetic field. Now, it always just boggles my mind a little when I think about this because the z direction is only defined by the direction I put an external magnetic field. It has no meaning without the external magnetic field. And so what's going to set it to be in one orientation? I'm going to go with one of the vagaries of quantum mechanics. So that's what this picture is illustrating. Now we're going to get to how do we get these numbers? How do we get the two equations in blue? Because it's kind of important. So first, we've already done this, and you're going to do it again in the homework. That's homework problem 2, doing all the commutators. So I won't spend too much time on these commutators because you're doing it. But at first, the angular momentum, I did this in class last period, this times the determinant of that, minus because of the Levi-Civita, and you guys you're almost done with the linear algebra. That should be snapped at this point. We're going to define a new angular momentum operator, a ladder operator. See the plus and minus? It has to be a ladder operator if it's got a plus. Doesn't have to be. We're going to define a new ladder operator. L plus is equal to Lx plus ILy, and L minus is equal to Lx minus ILy. And you might say, why? Right? Doesn't that seem like an odd thing to define? I mean, we didn't have an operator already or a Hamiltonian that this was based on. When we did the ladder operator before, it was based on a Hamiltonian, writing the Hamiltonian in a simpler way. We don't have that here. So the question is, why? Well, let's focus on the relationships. So let's do commutator relations. Let's do LZ, L plus minus. And this is part of the homework too. So if I do this, how am I going to evaluate this commutator?
You have LZ times L plus minus L plus minus LZ.
Okay. Now I'm going to substitute So I have that. What next?
Are we going to substitute in for the L, X, Y, and Z?
We are not going to, because we have commutator relations, right? You're finding all of these in your homework. And so that's why I didn't do all of them. But we have, right, here's actually the one we're doing right here. I should have done it in opposite order, and then I have the exact same thing. Obviously, I'm going to have minus sign because I did in opposite order. But we have these relationships between X, Y, and Z. So we're just going to rely on those.
Okay.
So what's next?
Well, your LZ in the first term addition. And in the second term, you're going to have to distribute your LX, LY.
I'm going to change colors for the second half. Just to make sure you're with me, minus plus means you're following the top sign. It's plus for the first one and minus for the second one. If you're following the bottom sign, it's okay. Just making sure we're on that one. So the reason I use the different colors is so I can separate these. So for the first one, I'm going to put from orange, LZ, LX, and then from blue, minus LX, LZ, plus I, and for the second one, from orange, actually, let me put the plus or minus out front. Notice because the minus plus means reversing or flipping the sign, that's why I have the minus sign in there. And with the plus or minus out front. But the things in the brackets become commutators. And so then I look at my answers here. LZ, LX is I H bar LY. And LZ, LY is going to be, since this is opposite order, change the sign. I times I is minus. Minus and minus makes it back to a plus. Everything has an H bar out front. So there, I found the commutator. Is that what I have down here? Oh, yes. It's in terms of the L plus minus, because the L plus minus, ILY, yeah, the L plus minus is LX plus or minus ILY. So my plus or minus, I need to move things across, but that gives me this relationship here. So that's how we get there. And yeah, I'm feeling a little uneasy about where my plus or minus is, but I think I did it all correctly. And I'm not going to go back and try to evaluate if I have that correct. It's all correct except for possibly where the plus or minus is. So we have a commutator relationship between LZ and L plus minus. Now, what if I did L squared and L plus minus? L squared, it turns out L squared with each one of the L, X, Y, and Z's is 0. L squared commutes with all 3 of the L's. Not doing it here, but it does. And since it does, then L squared is also going to commute with L plus minus. What does it mean if L squared commutes with L plus minus? That is if the commutator is 0. Actually, this is the one I wanted. What useful information can you get from that?
Can you say that the terms are, well, no, you can't say the terms are equal.
It has one basic meaning and then a lot of extensions. What's the basic meaning?
But order doesn't matter.
Okay, order doesn't matter, which means that they share the same eigenstates. Right, that means if I put the L squared operator acting on psi LMN, that gives me my L squared value times psi LMN, right? That's what it means to have the eigenstate. That's the eigenstate of the operator. Operator acting on the eigenstate gives me eigenvalue times eigenstate. And likewise, L plus minus acting on psi LMN is going to be equal to whatever its eigenvalue is. So I will put I'll put it without the hat to indicate this now eigenvalue. Actually, let me put a lambda sub plus minus just so it's a little clearer. So they both share the same states. That's an important thing. That means that there's no uncertainty relation between them. In fact, we saw the uncertainty relationship had the commutator in there. Right? If they commute, you have no uncertainty. You can know both of them at the same time. So L squared and this raising lower have the same eigenstates. L squared and Lx, Ly, and Lz likewise share the same eigenstates. But Lx and Ly and Lz all don't share the same eigenstates. That's a little confusing, isn't it? L squared shares eigenstates with Lx, L squared shares eigenstates with Ly, L squared shares eigenstates with Lz, but Lx does not share eigenstates with Ly, and Ly does not share eigenstates with Lz. So one of the things we have to do in our quantum mechanics is we have to say, okay, because I have this relationship, I can only choose one orientation to be the one I'm going to pay attention to. And so we default to saying, pay attention to Z. We could have chosen X or Y. It was an arbitrary choice. But we chose to pay attention to Z, which is why our ladder operator is defined not using Z, but X and Y. It's taking the other two that commute with L squared, but do not commute with Z. What does that mean in a physical sense? This picture on the right illustrates exactly what it means. We've chosen the Z direction. So the X and Y are the two directions perpendicular to vertical in this picture. What happens is when I put my atom in a magnetic field, the component that's parallel to the magnetic field is going to be fixed, but the components perpendicular are going to precess. So the magnetic moment of the orbital is going to be going around a circle with the Z component fixed, but the X and Y components alternating. That's the key of what's going on with an NMR spectroscopy. You put your atoms in a strong magnetic field. You put them in a strong magnetic field. The stronger the magnetic field, the faster this thing's going to precess. and then you use a radio wave and you test what frequency is going to be absorbed. Why would the frequency be absorbed? If it makes the magnetic moment flip from being like say you're in an L equals 1 state. If you change from M sub L equals 1 to M sub, well, actually we're looking at electrons in this case. Electrons only have plus 1/2 and minus 1/2. So for the electrons, it's real easy. You're flipping from plus 1/2 to minus 1/2. And there's a certain energy associated with that depends on the frequency at which it's rotating. So the stronger magnetic field makes it a higher frequency. And then you're probing how much is absorbed and that tells you how many electrons you have in there with that. Well, NMR, I got to go back another step. That's electrons. NMR is nucleus, right? The NMR is nucleus. The nucleus has protons and neutrons. The nucleus has its own spin state, and you're actually doing that with the nucleus. Yeah, I should have thought that one through, NMR, and started with nucleus.
So the nucleus, all the protons and neutrons inside have the same, magnetic moment?
Well, the magnetic moments, let's just go with spin. The relationship between magnetic moment and spin is multiplied by a constant, but that constant is different for a proton, a neutron, and an electron. So we're just going to talk about the spins and not worry about the magnetic moment because it's easier talking. So your protons, neutrons, and electrons are all fermions. Fermions are particles that obey Fermi-Dirac statistics. Fermi-Dirac statistics are the statistics calculated for the case of 1/2 integer spins. That is, your spin could be 3/2, 1/2, minus 1/2, minus 3/2, etc. But it doesn't have 0. So the key for the fermions is they don't have 0 spin as an option. If they don't have 0 spin as an option, they're going to behave differently than bosons. Bosons are things like, well, I'll put down one. Photons. Photons are bosons. The spin state for a boson is 0, 1, 2, minus 1, minus 2. They can have a 0 spin. Did you know that a photon has a spin? Kind of.
From what physics, yeah.
From what physics? Modern physics.
Modern physics,
Yeah. Because when you talk about the selection rules for decays, you have to have conservation of spin, and the photon is going to be carrying this spin, or this spin, I think it is. So you have to have, I have to think about it. No, the photon's always carrying a spin of 1. And so you have to have the change in L has to be 1 for the decay. And M sub L has to change by 1, 0, or minus 1. And so it limits which decays are possible for conservation of angular momentum. All right, how do I get on that? I don't know. I really don't. That's okay, we'll get back to this. Working with the ladder operators. These are the 2 commutator rules that involve the ladder operators. And these tell us 2 important things. The ladder operator does not affect total angular momentum. Because they share eigenstates, the ladder operator isn't going to change the total angular momentum. But it doesn't share eigenstates with LZ, which means it's going to change the orientation of the total angular momentum. So total angular momentum is like this. It's going to change when you use a ladder operator. But the total amount isn't going to change. It's just the orientation. So going back to our original position or picture, the ladder operator can shift it from one of these orientations to another one. And that is going to be our key to finding what they do. This is just explanation for the short words that were on the previous slide. So let's move on. Here's our proof statements. If I do L squared commutator with L plus minus, that's equal to 0. I'm going to apply that in the next line. So if I calculate L squared acting on the state of L plus or minus on LMN, on psi of LMN, then using the commutator relation, I can just flip the order, right? The difference in what's highlighted in yellow and what's not is the order has been flipped for the two operators. Because the commutator is 0, I can do that. It's no different. But L squared acting on psi LMN is going to give me my eigenvalue for L squared, whatever that is. And the eigenvalue is just a constant, so I can move it out. So that's equal to my eigenvalue times the state. So I'm saying, consider this the original state. There's the same final state, and I just have the angular momentum squared operator acting on my new state is equal to the original angular momentum squared eigenvalue times my original state. No difference there. So I did not change the total angular momentum by having my angular momentum squared operator acting on ladder operator psi. Now we're going to do the same thing, but using the LZ, which doesn't commute. So LZ, acting on this original state, I use my commutator relationship to replace LZ, L plus minus, with L plus minus LZ plus or minus H bar L plus or minus. And then LZ, okay, I'm tired of using a highlighter. LZ acting on psi LM is going to give me whatever the eigenvalue for LZ is, which I used mu to be consistent with the textbook, times psi LM n. And now I simply collect the terms again. And LZ acting on the ladder operator psi LMN is not equal to mu times the ladder operator. It's mu plus or minus H bar. So now we see, aha, we shifted the LZ value by using the ladder operator. We didn't shift the L value at all, but we shifted the LZ. So now we're going to put that in our pocket and come back to it in just a moment because I wanted to do these next calculations. One of these calculations is real simple. The other we're not going to do. We're going to use the ladder operator instead. So calculating the angular momentum, R cross P. Easy enough. P is minus I H bar del. Right? That's the three-dimensional linear momentum. And so using the spherical coordinates for del, I can calculate that my angular momentum vector is this beast, which isn't horrible. Angular momentum operator squared is going to be that acting on itself, which is the next one, which I'm going to consider reasonably horrible. We're not going to evaluate this one, at least not during class. And then my Lx is going to be using the definitions of unit vectors as shown here. I can take my, here is the amount in the phi direction, and here is the amount in the theta direction. And using those unit vectors, I can say, okay, well, this is Lx, Ly, and Lz. Lz is simple. We've already found the solutions, right? We found the spherical harmonics. We had that was our solution. And so my LZ, I don't even have to worry about this portion when I'm doing the LZ operator on psi, because that portion, the R function, is only a function of radius. So derivative with respect to phi does not matter. Furthermore, if we look at our spherical harmonics, all of our spherical harmonics have that. The only phi dependence is this here. So that means that LZ acting on YLM, actually I should make this psi, shouldn't I? If I take the derivative with respect to phi, what do I get?
I am times their stuff.
Oops. Okay, except for one thing. I forgot the minus IH bar. You kind of have to remember that too. I just did the derivative. Well, I times I is minus 1 times the minus is plus. So there we have it. The eigenvalues for LZ are really easy to find. And so the equation I start off with, remember the first slide, the cover slide where I said LZ is equal to MH bar. I don't, what did I say? No, it's hard to differentiate with my notation operators versus values. But the LZ value is just H bar M. That was easy. Wouldn't it be nice if it was so easy for the L value too? But it's not. So for the L value, where, oh, yeah, I just start right here. It's a more convoluted job involving the ladder operators to show that L squared is H bar L times L plus 1, psi NLM. So let's do that. Let's do it. I swear I thought I had that before these two, but I don't. L squared operator equals. And I will refer you to the textbook. I'm going to make sure that I write this down correctly so as not to lead you off into, the wrong area halfway through the derivation, because it's not super straightforward here. So the derivation that we're looking at is not there. On page 164. On 164, you see where it says the word now near the top? Right after equation 4, 111. That's basically where we're starting here. So we calculate L plus L minus so we can get this L squared. Or L plus L minus times L minus L plus. So if you do that, that's of course going to be Lx plus minus ILY Lx minus plus ILY equals Lx squared that minus plus ILX LY plus minus ILY LX minus, no, plus LY squared. I'm going to add and subtract the blue. Why did I add and subtract it? Because this here is L squared. And then that commutator, Ly, Lx, well, if we go back to the table of what we've already done, Ly, Lx is equal to minus I h bar Lz. Of course, just like with momentum, I have to check momentum position. I have to check the sign there. Get back to the page I was on. That page. So minus I squared is plus 1. And so that's what we get with L plus minus times L minus plus. And you're like, if you're a reasonable person, why did you do this? And the reason to do this is so we can write, L squared is equal to L plus minus L minus plus LZ squared minus plus H bar LZ. It's so we could do that. And you look at that, and once again, you should be saying, you know, Rich, I see that you've done some work, and I don't know why. It doesn't seem like I've made anything simpler. I've just made things more complicated. L squared acting on psi LMN. Well, we know that if I choose, let's say, I'm going to take the case of, not choose, choose M equals minus L. If I choose M equals minus L, then when I do this, I'm going to have now I wrote this, I wrote this out in a kind of doesn't matter form, but I'm going to choose one specific sign. Because I chose M is equal to minus L, we know that if I lower the state, I'm going to get 0. That is, it's not possible to lower the state from M equals minus L to M equals minus parentheses L plus 1. There's no state down there. So I'm going to choose just the top signs here. And in that case, this here is going to have to be 0. Because I had first the L minus operator acting on it, and L minus acting on the bottom state has to give me 0. I can't go to another state with M having a bigger magnitude than L. So that gives me 0. And then I'm going to have my LZ squared. Well, we've already worked out that's going to be H bar M squared. right? Now we're going to do it again. Choose M equals plus L. So now we're going to choose the top possible orientation, the top possible L. And I'm going to switch to using the opposite signs, the top signs. Because I switched the signs, this is a plus for the last term. And so just as before, I can't raise from M equals positive L to a higher L or a higher M. And so this has to give me 0. Notice I'm only evaluating the first one because it's the one that acts first. Once I have 0, it doesn't matter about the other one because it's 0. Okay, so there I have 2 different results. Now, if you look at these, one has a plus M, or M plus one has an M minus 1. And you might start to feel like we've really hit a problem. But a key here is the L squared, the total angular momentum is only depending on the L variable. It doesn't matter if it's what the orientation is, it's the L that's telling us the total angular momentum. And so these 2 answers have to give me exactly the same angular momentum. And of course, we had chosen here for the top one, M was minus L, so L is equal to minus M. Well, actually, let's do it the other way. M equals minus L, so I'm going to substitute that in. If M is minus L, then this is H bar squared times minus L minus 1. Factor out 2 minus signs. Likewise here, this was M equals L, so of course it's equal to H bar squared L. So in both cases, what we found was angular momentum operator squared acting on psi LMN gives H bar squared times L plus 1. So from this, I conclude then that L is equal to square root of that. Why didn't I put a plus or minus sign? Yeah, because we're only looking at the magnitude. Right, the magnitude of the angular momentum is given by this, and then the orientation, what orientation information we have available to us, because we can only tell one of the 3 orientation components, is given in the lowercase m. So there we have the eigenvalues for angular momentum, total angular momentum. So you can see a derivation here using the ladder operators, because you know what, this work right here is much easier than taking that highlighted operator and having that operate on a spherical harmonic. I hope you agree with me on this, especially to show that it in general is true and not for a particular specific case. Let me share a very sad story. Last week, we had for our senior math majors, they had to give presentations. One last Wednesday, one this Wednesday. And one was on examining the spectrum of, what was it? The spectrum of symmetric operators. I was like, oh yeah, this is totally awesome. This is exactly what we're doing in quantum physics. She was just restricting herself to real symmetric operators instead of Hermitian operators like we're using, but it's just a subcase. Oh, she did all her math wrong. And yeah, it was very disappointing. But what we're doing here is finding the eigenvalues for the eigenstates, and they have to be real and so on. I shouldn't say anything more, but she apparently didn't understand the word normalized. She had in her practice work 2 of them. Hey, I didn't do that. Lights went out because of motion. She had 2 of them as normalized eigenvectors, and the third one she had the null vector. What happens if you transform and you have the null vector? I'm pretty sure it doesn't transform right. And then when she tried to do the work, I stopped her and said that we can't use the null vector. We have to actually use the eigenvector for the third state. And I think that broke up her process because then she didn't normalize anything. And you guys would be better students at this, okay? Let's talk about the means of the quantum numbers for 2 minutes and go home. So first, the principal quantum number primarily tells you the energy and the size of the orbital. Primarily, it's not the only thing that tells you energy. At this point, you would believe it does tell you the entire energy, but we haven't finished. N equals 1 we call the K shell. So in spectroscopic notation, when you see that capital K, so like in X-rays, if you have the K alpha characteristic line, that means that it's falling down into N equals 1. Alpha means that it's delta N equals 1. So if it's a K beta, the beta is delta N equals 2. And so a K alpha is shown there. And there's the K beta. So if you look at the characteristic lines in X-ray, that nomenclature is something we can understand based on our quantum numbers. Capital K, N equals 1. Capital L, N equals 2. Capital M, N equals 3, and so on. And so if it's an L beta line, that means it ends at 2, and it had a change in 2, so it went from 4 to 2. Then the L's tell us the total angular momentum, and we have names for those based on what people saw when they looked at the energy spectrum of atoms. And so L equals 0 is called an S orbital because it was sharp. You had sharp lines in the spectrum associated with S orbitals. P principal, I'm not sure where that comes from, but P is for L equals 1. D for diffuse, more spread out, for L equals 2. F for fundamental, for L equals 3. G, I was wrong last class period. It's J that's omitted, not I. I thought it was I omitted. It's J. So you just go through sequentially, alphabetically after that. So if you say, it's a P orbital, you should in your mind say immediately, P orbital, that means L equals 1. S orbital, L equals 0. Those should go back and forth easily in your heads. And then we have that magnetic quantum number that's just telling us the orientation. So those are the quantum numbers that we've been discussing. Now we're going to add one more quantum number, in class on Wednesday, and that's where we're going to start talking about the spin on Wednesday. And so that will be the fourth quantum number. And in that case, oftentimes we talk about m sub s for spin and m sub l for the magnetic quantum number. Why they both have an m? Because they both show up when you put it in a magnetic field. You don't see the effect until it's in a magnetic field. And we have L here for the total angular momentum. We'll have S for the total spin. For the electron, the S is always the same value. It's 1/2. So nobody ever talks about the S because it's always 1/2. But the M sub S can be plus 1/2 or minus 1/2, using the same rules that M sub S has to be between plus and minus S. Okay, here's the other things we've seen. It's time to go. See you Wednesday. Or actually, I might see Indy tomorrow. If you're not going to be there, let me know just so I don't get set up.
Yeah, I'll send you a text.
All right, thanks.
Yeah.
Oh, Indy, you don't know how to set up for it, do you? For the Zoom stuff?
I'll struggle.
Okay, thank you.